All right, so let's continue on to chapter 22. Chapter 22 is dealing again with carbonyl chemistry, but it's a completely different type of carbonyl chemistry. This chapter is focused on the alpha carbon. So if we think back to carbonyl groups, we've got a bunch of different positions off of them. The first position right next to a carbonyl group is called the alpha position. One away, we've got beta, and then we've got gamma, and then we've got delta over here. This entire chapter is going to focus on the alpha position. And the unique thing with protons in the alpha position is their pKa. So the pKa of an alpha proton is about 20. I'm just going to ballpark it. The pKa of most CH bonds is closer to 50. So it's 30 orders of magnitude different. Does anybody have an idea why? Yeah, exactly. So if we pull a proton off of the alpha position, that conjugate base is stabilized via resonance. So let's take a look at what's going on here. And we can say reaction with strong base. So let's take just regular acetone. And I'm going to draw in one of these alpha protons, and I'm going to have it react with the strong base. This base can come grab the alpha proton and dump electrons down onto that carbon. Because this is an acid-base reaction, I'll draw equilibrium arrows, and I'll even draw in these other hydrogens. So now we have a carbanion, and this carbanion can delocalize and kick electrons up to that oxygen. Oh. There we go, it has a negative charge now. And this has a unique name. It looks like a functional group we saw in our alkyne chapter. We've got an ene and an alcohol. What was that called? Enol. An enol. This time we have an oxygen with a negative charge. So this is called an enolate. And this is going to be a big focus in this chapter, is this resonance stabilization allows for a unique chemistry to occur in these molecules. All right, but we can also see these reactions occur with acids and bases too that are slightly different. So let's see the reaction with catalytic acid. And this should be a review a little bit from our alkyne chapter. If we have a ketone with acid around, we can protonate the carbonyl. And that turns it into a good electron acceptor now. And we still have these alpha protons over here. And we've created water. So this water can act as a very weak base. Grab one of these alpha protons, clamp down, and kick up electrons. plus we recreate our acid, which makes this entire system catalytic. So we said from previous chapters we call this an enol, because it's the mixture of an alkene and an alcohol. And we also saw that we can do this keto enol tautomerization with base, so let's quickly review that. And when you have base around, you can immediately deprotonate one of these alpha protons. So in this case, I'm just going to arbitrarily choose OH minus as our weak base. Oh, let me stick with red. And we can kick electrons down, and we said that the intermediate that we make is resonance stabilized. And we also have water around that was recreated from our base. Let me slide this over a bit. And we can just protonate this oxygen. And in both of these cases, we end up with our enol, and we recreated our base, making it catalytic again. All right, so, yep, I'm looking down.
So for the resonance part, could you just show the enol, or do you want us to show the resonance?
You can show both. I mean, you can show any resonance structure and technically be right. The reality is there's major contributors and minor contributors. So in this case, what do you think the major contributor is? The right side or the left side? The right side, and why is that? Yeah, the oxygen's electronegative. It's happy with the negative charge. Carbon's not that electronegative. It doesn't want that negative charge. So in this case, the enolate is the major resonance contributor. So I'd prefer to see that. But you can draw it either way if you want.
Well, no, I was just saying instead of showing the resonance, I'd rather show like enolate part.
Yeah, and some people will show this first step using multiple arrows too. So they'll add in a third arrow and just go straight to the enolate. Yep. All right, so now the question I want to get back to is when we covered the alkyne chapter, I told you guys that these reactions tend to really, really favor the ketones or the aldehydes. They don't like to be in the enol state. That was kind of a half-truth.
Oh my God.
And this goes back to a little bit of what we talked about first term. I didn't lie.
No, half-truth is lie.
It's all a matter of perspective. Equilibrium positions depends on stability. And let's take some examples of what I mean here. Let me fix this line. All right. If we have a generic vanilla ketone, like cyclopentanone, we could imagine it tautomerizing to its enol form. But I told you guys that ketones more or less are the favored form. And in fact, if we were to draw the equilibrium arrow for this tautomerization, it would very, very much favor the ketone. You can actually measure this by NMR and see the amount of each in equilibrium by measuring the alkene proton and integrating it compared to all the other positions. And when you do this, what you'll see is you've got 99.99% ketone. So see, I wasn't lying to you guys. Most of the time, it does favor the ketone form. But let's take a different one. So we've got 2,4-diketone. In this case, we can draw the tautomerization product and include the enol next to it. And let me actually clean this up a bit. There we go. So we've got the enol form. What's special about the enol form? A couple things. One thing is, if you look at these bonds right here and here, what do we call those when we've got double bonds separated by a single bond? Conjugated. So in this case, the enol form is conjugated. And there's also another really unique feature going on here. Does anybody spot it?
Could the oxygen attack the carbon?
It's not exactly an attack, but we do have a lone pair. And so what happens is you get intramolecular hydrogen bonding occurring, and that's highly stabilizing. So in this case, we get an intramolecular H bond. So if we look at the tautomerization equilibrium here, it actually favors the enol form slightly. And if you were to look at this in an NMR, depending on your solvent, you'll get 70 to 90% of your enol in equilibrium and about 10 to 30% of your diketone. All right, let's take it one step further and see a case where the enol is almost exclusively preferred. So we can draw the enol form for this guy. And which side of the equilibrium do you think is favored here?
The right side.
Yep. Yeah?
When you said conjugated and the intermolecular H bond,
Mhm.
does that mean that it has a resonance, another resonance structure for that?
Yeah. So when we went over conjugated molecules, we said that they're very unique because of all of the resonance structures that they have. So alternating double single bonds tend to be highly stable, and they have unique reactivity. All right, so the last one, we said the right side is more stable, and why is that? It's aromatic, right? So it's a special type of conjugated. And in this case, if we were to measure this in equilibrium, this would be 99.99% on the enol side and practically none of the ketone in solution. So under most circumstances, you'll observe your ketone, but there will always be, even in this top example, a very, very small percentage in equilibrium that is your enol form. It's just not highly favored in equilibrium. It's going to be 0.001%. All right, so now let's look briefly at the reactivity of these.
How did you just write ketone?
Oh my gosh.
I'm like, wait a minute.
Aromatic.
Okay.
I can't do two things at once. Aromatic. So now let's look at the reactivity of these. Of enols and enolates. And so I'm going to draw an enolate here. So we've got our oxygen with the negative charge, and it's got a resonance structure where we could have that negative charge down on the carbon. So these are two valid resonance structures. And we can imagine these each reacting with an electrophile. So I'm going to call this electrophile E+, And I'll do the same down here. Oop. So if we were to have our nucleophile attack our electrophile, it could occur either at the oxygen or it could occur at the carbon. And so let's draw out both products that we would get. And then we'll add in our electrophile. And so with alpha carbon chemistry, you see it occur occasionally at the oxygen position and occasionally at the carbon position. And we'll go into this in much more detail as the chapter goes on, but it's important to remember when you deprotonate the alpha position, you're actually creating a nucleophilic site that's spread across two different atoms. Yeah?
Does that give me a picture?
Not always. You can control this, but it depends on the specific reaction. There are various ways we can control it. All right, the last thing I wanted to cover in the intro was how to choose an appropriate base. And this goes, again, back to first term. I know a lot of us are a little bit rusty on our acids and bases, so I wanted to go back to that. And the easiest thing to remember for this is you can determine the pKa of your alpha proton. The pKa of this alpha position should be less than the pKa of your base's conjugate acid, and this should be less than the pKa of your solvent. And this is an ideal situation. Yep.
Are you going to give us a chart? Or are you going to give it
We'll go through these. There's one very, very common reagent, but I wanted to show you guys a few of them and kind of practice this a bit.
That's how we avoid the hydrate, right? I was looking at above before you started this, like, why doesn't the water attack the ketone?
Yeah, you can try to control it by choosing your base appropriately. If you choose a really, really strong non-nucleophilic base, it'll just do deprotonation as opposed to attacking the carbonyl. And so we'll get into that.
Okay.
Yeah. All right, so let's take some examples. Let's say we've got acetone, and the pKa of acetone is 19.2, and we react this with hydroxide. And then ideally what we would want to do is deprotonate that alpha proton, give it a negative charge, and make water. And the pKa of water in this case is 15.7, which in this case means that water is more acidic than our alpha position, right? So which side is the equilibrium going to favor, the right side or the left side? It's going to favor the left side, right? Because if water is more acidic,
Wait a minute. Why is that?
so remember this, the stronger acid is going to push the equilibrium, right? So lower pKa means stronger acid. It's going to push the equilibrium this way, which means that hydroxide isn't going to be a good base for doing this deprotonation.
Okay, but remember what I was asking you in lab about that question, and you said, oh, it's like acid base. The more stable, it pushes towards the more stable one. So that's opposite. No, never mind.
All right. I like when I don't have to explain things. All right, so hydroxide isn't a good base, but the important thing to remember is there is still some of the enolate in solution, right? just a very, very small amount. We can take a look at a different example. Let's go back to our diketone example. And we can use hydroxide. And if we were to deprotonate the alpha position, we said that that middle proton is actually fairly acidic. So now we have a negative charge there that's stabilized via resonance. And we create water. So the conjugate base, or conjugate acid of our base is still water, which has a pKa of 15.7. If you look up the pKa for your diketone, it has a pKa of 9. So which way is the equilibrium going to lie now? To the right. So in this case, hydroxide could be a pretty decent base for that deprotonation, but the one above it, it's not a great base.
Wait a minute, what'd you call it?
So again, if we look at this, lower pKa means a stronger acid, more willing to donate protons, which means the equilibrium is going to favor this side. So stronger acids will push the opposite direction.
Oh, okay.
All right, now let's take a look at one last example. And this kind of goes back to Eddie's question. In our top case, when we have hydroxide around, we could also run into a competing reaction where we form hydrates. So oftentimes what chemists do is they want their base to be non-nucleophilic. And in this case, we're going to use a special one. It's a lithium salt. And what would this be called? It's lithium. And what do we call the alkyl groups on there? Yep. It's lithium diisopropyl amide. So let's write that down.
Common reagent.
Yep.
Is there a short name for that?
Yep. LDA. It's much, much easier than writing out lithium diisopropyl amide every time you want to use it. So in this case, we can do the same reaction. We can try to deprotonate our alpha position, get a negative charge. And in this case, we end up forming an amine as our conjugate acid. And we can go through and find the pKa of our conjugate acid. And in this case, the pKa is 36. And there's still a lone pair on there. I'll go ahead and draw that.
Would it not have
Oh, sorry. Oh my goodness. There we go. Good catch. All right, so it should be neutral, not charged. And in this case, the pKa of our starting material, again, is 19.2. So in this case, it's definitely going to favor the product side. That's a huge difference in
I
pKa.
got it now.
So why is lithium diisopropyl amide commonly used for these? Yeah, it's super big and bulky. It's not going to have a very easy time squeezing into that carbonyl. It will, on the other hand, have an easier time abstracting an available proton in the alpha position. So in this case, it's an appropriate base to choose. All right, so now let's, yep.
Can you use Carboxylic as that?
So let's think about that. I'll actually pull up the class webpage too and show you guys one thing. So last fall, I gave you guys, oh my goodness, I've got fat fingers. Here we go. If you go in the useful links section, you can pull up the sheet that I gave you last fall. It's under useful charts, common bases and solvents. And if you go here, you can look at the conjugate acid of tertbutoxide. It's 17. So in this case, the pKa is 17. The pKa of our alpha position is 19. So would we want to use terpetoxide? No, it wouldn't be a very good base. So you can go back and refer to that chart if you need to. I copied it over to the this corridor's website.
Isn't that an amide and not an amide?
It's weird that they call it amides, and to be honest, I'm not sure why.
I think it just said amide on the table, the other one. Plus, there's no carbonyl group, so it can't be an amide.
I'll double check on that. I think it's an amide.
Pull it up.
Pull it up?
Yeah.
I might have even typed it in wrong on this chart. I'll double check to see which one's right. I think it's an. I know. I think I might have made a typo on there. I'll double check though. All right. So let's continue on to alpha halogenation. This is the first reaction we're going to see with the alpha position, and it's pretty straightforward. So let's do acidic conditions first. And we'll do the overall reaction, and then we'll go back and do the mechanism. So if you've got a generic ketone, you can add in a catalytic amount of acid. And in this case, I'm going to use bromine as our halogen. When you do this, you can install your bromine directly onto that alpha position, and your byproduct is HBr. This isn't the world's best reaction. Typically, it's 65% yield, and we'll talk about a little bit of why this is a problematic reaction in a second here. But let's first do the mechanism. So if we have our ketone and our acid, what's going to be the first reaction here? Protonation of our carbonyl. So we can show the carbonyl grabbing a proton, kick off water. Now we've got water around that can deprotonate our alpha position, and that will give us our enol. And so these are all under equilibrium conditions. But if we've got bromine around, we said that that carbon can actually be somewhat nucleophilic. So I'm going to show this as a two-step or three-step arrow pushing. We'll take this lone pair, dump it down, this lone pair, dump over onto that carbon, and then that carbon will attack the bromine and kick it off there. So it's a bit steppy. And now our oxygen's protonated. Another equivalent of water. I'll also draw Br minus over here. Can come and deprotonate our carbonyl. Nope. The problem with this reaction is that if we look at our alpha position where the bromine's attached, it still has another proton on there. And that proton's even more acidic now because of the halogen pulling the electron density. So oftentimes this will continue on, and you'll end up with your dibrominated product. So the one caveat with this reaction is that it often results in over-bromination. And that's why the yields sometimes are considerably lower than what we're used to seeing for these. All right, let's go through and do an example with one of these. So we're going to add in acid and bromine. So this looks exactly the same as our previous example. I just added on a methyl group. What would our product be?
When you add to the benzoic acid?
Yeah.
There's no aromatic ring. What do you mean benzoic?
Oh, right there with the methyl group, yeah.
So let's take a look.
I don't know. Or I could do either, though.
So let's first draw our enol.
Is it preferable substitute?
Oh, shoot. So we can get both enols, right? Which enol is more stable?
On the left.
The one on the left, why? More substituted, right? So we can show this reacting with Br2 and this one reacting with Br2. I'm not going to show the full arrow pushing mechanism.
Is it a matter of like kinetics versus thermodynamics though?
Not necessarily. It's just a matter of major versus minor. So in this case, we've got a major product here.
Yeah.
Oh, thank you. Major and minor. So in this case, because the one on the left is the more stable enolate, it'll prefer to go through that pathway, but you do still get a little bit of your minor halogenation occurring on the opposite side.
Can it over halogenate also?
In this case, if we look at our major product, there are no more protons on that position where the halogen added, so you don't run into that problem as much when you are on a more substituted carbon. Tertiary carbons are often preferred, especially if you don't want to over-halogenate. All right. So now let's take a look at another reaction, this time under basic conditions.
Can you do that with like chlorine too?
Yep. Oftentimes chlorine, though, is a little bit more problematic because it's a gas. But I'll show you guys an example of a shortcut around that too, just in a little bit. Yeah, chlorine gas cylinders really scare me. They're one of the most frightening chemicals to work with because they corrode everything, including the cylinder that they're housed in. So you have to store them in special cylinders, and the heads get all rusted and gross. It just makes me nervous. So I prefer to avoid reactions with chlorine. All right, so let's take another example. This time, if we react this with sodium hydroxide and bromine, we can still get bromine to add. And again, you still run into this problem of over-bromination, even more so with the basic mechanism. and let's quickly take a look at it. First step in this case is just deprotonation of our alpha position. And I know I said that this equilibrium is not favored, but it works well enough where even that 0.01% that's around in solution is enough to do that nucleophilic attack. Oop. And in this next step, the oxygen can dump down, dump over, attack the bromine, and kick off bromide. And voila, you end up with your halogenated product. So it's a pretty simple reaction. There is a cool variant of this, and I wanted to show you guys that too. And this can be done with carboxylic acids. This is alpha bromination of carboxylic acids. It's a variation on all of this. The formal name of this reaction is the Hell-Volhard Zielinski reaction. They couldn't give one guy credit, I guess. They had to share it. Yeah, that's a rough last name growing up, I bet. Oop. All right, so in this reaction, you've got a carboxylic acid. Carboxylic acids still have alpha protons on them. But the first step in this reaction is we need to turn it into an acid halide. Specifically, we need to turn this into an acid bromide. Can anybody think of a reagent we could use to convert the acid or the alcohol into a bromine?
PBR3.
Yeah, PBr3. So that can work for making acid bromides. Then in the next step, what we do is we can tautomerize this. Into our enol. So we interconvert between our acid halide and our enol. So let's write that down. And this is simply referred to the acid halide enol. Doesn't have a new special name. Now the nice thing with this reaction is that you can do the alpha bromination. So this oxygen will kick down, kick over electrons, and attack the bromine. And then in the last step, during your reaction workup with water, you can not only deprotonate that carbonyl, but what happens to your acid halide? Yeah, it goes back to your carboxylic acid, right? So acid halides can be converted back to their corresponding carboxylic acid just by treatment with water. But now we've got a bromine coming off of that alpha position. Do you guys think this reaction occurs with stereoselectivity? It occurs in the exact carbon on the alpha position, but do you favor R or S? No. So if you think about it, after this first arrow and second arrow, you have a carbanion. The carbanion is trigonal planar, so you can have attack occur from either face. So you lose stereochemistry there, but oftentimes this is just a useful intermediate for further reactions and synthesis. All right. I think we have enough time to cover another reaction.
Oh, you said we were going to barely start.
Barely start. This is just scratching the surface.
Yeah, Adrian, there's probably like
How are you
60
trying to catch up on
reactions in
book
this
problems?
one, like there was in the last chapter. It's just in the last.
This is one that most of you have already seen, and it's called the haloform reaction.
You should ask one question too, right?
And I'm going to draw in 3 hydrogens here. So in this reaction, it's kind of neat. I'm going to just draw one-way arrows, even though we know it's all under equilibrium. Screw it. I'll do regular arrows. We can take sodium hydroxide and deprotonate. Let me include all my arrows. Whoop. We end up with our enolate. And then if you react this with bromine, this should be a one-way arrow, sorry. Oh my goodness. Br minus. Sorry. This should be Br2. I'm getting rattled up here. And then that carbon can attack our bromine, and again we get our alpha halogenation just like we've seen before. And I'm going to just write times 2. We have 2 other alpha protons that we can continue to deprotonate and halogenate, right? So I'm not going to draw out all of those steps. But what I will show you is the intermediate that we get from this reaction. Oop. There we go. And if we have hydroxide around, hydroxide's unique because it's a good base, a reasonably good base, and it's a good nucleophile. So what could it maybe do? What was that? We don't have any more alpha protons, so it can only do something nucleophilic. Yeah, it can attack the ketone, exactly. And then in the last step, we can take this oxygen, clamp down, and then actually kick off a carbon in this case. Why is carbon an okay leaving group in this example? Yeah, it's got 3 bromines on it sucking electron density away, so in this case it's a decent leaving group. And so this bromine still, or this carbon still wants its proton, so it'll steal it back from the carboxylic acid. So, yep. Oh, sorry. Thank you. And then during our acid workup,
Don't say we're gonna protonate it.
yeah, we protonate it.
That is just, excellent.
So it's a two-step reaction. The first step, you react it with sodium hydroxide and bromine. And then in your second step, you need to protonate your carboxylic acid.
Are all these in equilibrium?
Took it away and then you're putting it back, but I don't know.
So it's a two-step, two-pot reaction, right? So in this case, we go to our carboxylic acid. And the cool thing is we can get there from a methyl ketone. So we can interconvert from a ketone to a carboxylic acid.
Are all these steps in equilibrium?
Anytime you have the proton transfer, it's going to be in equilibrium, but it is a thermodynamic sink as soon as you get to the carboxylate, which is why I switched to one-way arrows. Yeah. All right, the place where you may have seen this reaction was in lab. You guys had a methyl ketone. And what you did was you added in chlorine gas and NaOH. And I'm going to put chlorine in quotes there. And then in the second step, you reacidified your product in order to get to your carboxylic acid. We didn't give you guys each chlorine gas cylinders. How did we get chlorine? Bleach. So if you take NaClO plus NaOH, you can actually use that to make a small amount of chlorine in solution, and so that chlorine was what you guys used to do your own haloform reaction, and you guys converted your methyl ketone to a carboxylic acid. All right, before we leave though, why did you guys add in acetone at the end? What's the use of doing that? Yeah, right? So would it be fun to take a waste jar out of your hood when it's fuming chlorine gas? No. So instead what we did was we added in acetone, and the acetone chewed up all that excess chlorine in there, and we made acetic acid, which is nice and innocuous, and then we dumped that down the drain. So we use acetone in order to remove any of the excess chlorine in there. This is also a good important thing to bring up for at-home cleaning. If you take bleach and drain cleaner and mix them together, you will probably poison yourself. And occasionally you hear people doing this where they try to get really inventive and they're like, you know what I'm going to do to clean this drain? I'm going to throw everything at it. And then all of a sudden they start choking and they don't feel very good. This is why you don't want to do that. You don't want to create chlorine gas unless you absolutely mean to create chlorine gas. So that's where we'll leave it today. We'll continue on in chapter 22 next Monday. Just a second.